Good afternoon. I'm Steve Thompson. I'm here to present our talk, Enhanced Surgeons Understanding the Design of Augmented Reality Instructions for Keyhole Surgery. I'm presenting on behalf of Christoph Davis, who couldn't be here. So let's talk about keyhole surgery. Brief introduction for those who aren't familiar. Keyhole surgery is minimally invasive surgery, and so instead of cutting the patient open and operating directly, we operate using cameras and pivoted tools. There's a picture here of our experimental setup, so this is obviously not a clinical example, but this is what we had down in our lab. We can see the person on the left of the image is trying to perform a procedure using a laparoscopic pivoted tool inside the plastic torso on the table in the middle of the picture. And to perform that procedure, they are looking at a screen in front of them with a camera feed from a laparoscope. You can see the laparoscope in the middle of the image. It's the thing with a cable hanging off it. So the important point is, although the incisions are smaller, so it's better for the patient, the surgeon can't see as much. They're only able to see a small amount of the patient's anatomy through a small window on a video screen. They have a limited field of view. They also have quite poor ergonomics. A skilled surgeon gets used to this, but there's still a mental load cost to trying to operate in this way. So what we're about is trying to help surgeons perform keyhole surgery by giving them more information, giving them more relevant information. So we're trying to use augmented reality to do this. On the left here, we have a picture taken from an example, a clinical example, where we have a couple of surgeons looking at two screens. So on the right-hand screen is the sort of basic raw image. And on the left-hand screen, we've introduced augmented reality where we're showing patient anatomy derived from CT scans, so the surgeon can hopefully understand the anatomy better, even though they've still got only a small window to operate through. And on the right of this slide, we have a sort of close-up of that screen. This is from earlier work on the smart liver system, where we have liver overlaid with rendered anatomy using some various techniques, outline rendering and depth fogging, to try and convey depth information and make a nice, easy image. But what's an unknown question, and what we're trying to build a research pathway on, is trying to design that augmented reality system to maximize the benefit to the surgeon and to the patient. So here are some examples. On the left, we've got no augmented reality. In the middle, we've got the example we just showed you with outline rendering, depth fogging. And on the right-hand side, we've got basically the same image, or very similar, but just showing sort of plain opaque surfaces overlaid, which, as you can see, tends to obscure actual anatomy. So the question is, which of these methods is best? Which is going to have maximum impact on surgery performance times, side effects, etc. So we're trying to use set up a research program looking at how we can measure this sort of stuff in the lab and use those different design decisions to come up with the best way to design an augmented reality system for surgery. So factors we're trying to look at is task completion time. How long does it take the surgeon to perform the operation or a specific task? Operator comfort. Can they look at these images without eye strain or whatever? For a surgeon, they'll be spending on a per case might be 2 to 3 hours. So you need to be able to look at these images for a long time. And then the other thing we're looking at is distraction. So we're showing these images to the surgeon. Just showing the images to the surgeon causes them to miss other important detail. And what we're trying to do is test these things in our lab. It's very difficult. You can't just go into an operating theatre and test these things on people. So we're trying to build a research program where we can test these things in our lab in a structured way and feed that through to ultimate design decisions. So So we've made an abstract and simplified experimental setup. We've got a nice piece of software, Psychic Surgery Basic Augmented Reality Demo, which is open source software, which enables us to construct a augmented reality system. It can use surgical laparoscopes and take a video feed from them. It can use surgical tracking systems like electromagnetic tracking systems or optically infrared optical systems. Or in the example we used in our lab, we're just using Aruco tags, which you can just see in this image of our paper phantom inside our plastic torso phantom. So we've got this software running. This is our physical setup. We've got a plastic torso phantom with a neoprene sheet on top, and going through that neoprene sheet is the laparoscope camera and a pair of laparoscopic grippers. Inside the plastic torso phantom, we have just a printed on photographic paper, a representation, a slightly abstract representation of a human liver. We wanted to abstract because the people we wanted to recruit for this experiment, we wanted to recruit unskilled people rather than skilled surgeons. So we want something slightly abstract. On the right, we've got the augmented reality display. So it's showing the feed from the laparoscope overlaid with a wireframe model of the anatomy with a target for where the marble is. And we're getting the participants to try and extract that marble under augmented reality guidance. We tested this under various conditions. So the test is pick up a marble. We recruited 12 participants. These were just colleagues and students in our own department. They weren't trained surgeons. We used 3 different overlay colors, red, green, blue, 2 surface representations, surface and wireframe, and 2 levels of opacity. These values basically chosen based on what people are doing in the literature. There's more advanced ways to do it, but at this stage we just wanted to keep it fairly simple. Things we measured, task completion time in seconds, and we collected a lot of qualitative data via questionnaires, NASA TLX scores, etc. On the other, so the last thing we were interested in is, I mentioned earlier, inattentional blindness. So we added a plastic spider onto the phantom, which you can see in this image. And that was there throughout our experiment. At the end of the experiment, we asked the participants if they noticed this. And what we were looking for was, we're doing all this augmented reality, does having that potentially distract from what else the surgeon should be looking at? We used a spider because we did try early on using more clinically relevant things like a misplaced surgical clip, but our participants, being not skilled surgeons, just didn't pick up on that. They didn't realize it was out of place if they saw it. Results. So we were able to do this study quite quickly. The study design was basically sound. Results are inconclusive. We didn't have enough participants at this stage, but we've got a setup where we are going to be able to recruit significantly more. We did see a significant training effect on participants, so the first time they ran the trial would be significantly longer than subsequent trials. I think we got each participant to do it 3 times under different conditions, randomized orders. So we were able to get quite a good amount of data. But for future work, we need to work on training them first. Only 1 person out of 12 actually noticed the spider, which indicates we demonstrated that intentional blindness was occurring, but it would be nice to get the balance between occurring and not occurring better. So ongoing work, we're doing more experiments, tightening up our controls and our training, and bringing in different visualizations, and getting a more obvious distraction, a more obvious spider, if you like, to see if we can get more people to notice it and then balance it out. So we've shown we can use our software to perform representative experiments with unskilled volunteers in our lab, and early results indicate that we do see a learning effect and the occurrence of inattentional blindness. Thank you very much for listening. Goodbye.